Okay, so welcome back. I hope you had a nice break. So now we are going to look at fracture with slightly different eyes. We are going to look at energy methods in fracture. The ideas that we are going to talk about were due to Griffith, given exactly 100 years ago in a seminal paper in 1921. We are going to talk about it in more formal way than Griffith did, but the ideas more or less are exactly the same as he fleshed out in his paper. So, so the basic idea here is that a crack grows when it is energetically favorable for it to grow. Uh, what do we mean by that? Is the following. Suppose I have a body in state 0 which goes to state 1. The difference between state 0 and state 1 is that state 0 had a crack with a crack area of A, whereas state 1 has a slightly higher crack area, A plus delta A. So the crack has extended. And Griffith's idea is that this transition will happen spontaneously provided state 1, going to state 1 reduces the total potential energy of the system. So if you remember from your elasticity courses, the total potential of elastic system is the strain energy stored minus the potential of the external loads. So the potential of the external loads in state 0 are these terms. So this is the traction applied on the body at state 0, displacements on the surface at state 0 integrated over the whole surface gives the total potential of the loads due to the surface tractions, whereas this gives you the total potential of the loads due to the body forces. So this is the potential of the loads. Whereas W is the strain energy density function, and if you remember, it is defined as the scalar function of strains such that its derivative with respect to the strain gives the stress. So there's a unique strain energy density function for many materials, and for elastic materials in particular, this is a quadratic function of strains, and therefore the derivative with respect to strain gives a linear function of strain, and thereby this relation is another way of stating the constitutive equation of the material, which for linear elastic materials is that stress is linearly proportional to strain. So this is another way of stating, using a quadratic strain energy density function is another way of stating the fact that stress and strain are related linearly in linear elastic fracture mechanics, and strain energy density is half sigma ij epsilon ij for an elastic material and has units of energy per unit volume. So this is units of energy per unit volume. So energy per unit volume times a small volume dV gives you the total energy in that volume, integrated over the total volume of the body gives you the total strain energy stored in the body. So total strain energy stored in the body minus the potential of the loads gives you the potential energy of the system at state 0. Potential energy of the system at state 1 is this, but in addition to the mechanical potential energies that are due to the potential of the loads and the strain energy stored, there is also this additional energy cost of forming these crack extensions. So these crack extensions, we assume that uh, GC is a material property which is equal to the energy required, the surface energy required to form a unit area of crack. And this is a constant for the material. So GC times dA, this is the total energy required to form dA amount of crack. And since the total amount of crack area formed is delta A, integrating this over delta A will give you the total energy expended in forming the crack. So if the potential energy of the system in state 1 is higher than the potential energy in state the potential energy in state 0 is higher than the potential energy in state 1. Remember, potential energy in state 1 also includes the cost of forming the crack. If this is the case, then the crack will form. Crack is forming because by forming the crack, you are able to lower the potential energy of the system. Call this pi naught, call this pi naught, the potential energy in state 0, call this pi 1, potential energy in state 1, and assume that delta A is small so that this integral can be replaced by gc times delta A. If you do that, then you have delta pi, which is pi naught minus pi 1, the decrease in potential energy due to formation of the crack, plus the energy required to form the crack, that is delta A times gc, has to be less than equal to 0. So this is the condition. This is the condition for the formation of a crack in an elastic system, according to Griffith. So we can take this a little bit further. Suppose the crack growth takes place without any change in the potential of the loads. So then in that case, delta pi is equal to delta U, which is the change in the potential, change in the strain energy stored in the system. So this is the strain energy stored in state 0 minus strain energy stored in state 1. This is the case when the crack grows in spite of the fact that there is no potential of the external loads. The external loads don't change. The crack is growing spontaneously. In that case, this is the condition for crack growth. And we can take this delta and make delta A tend to 0. Then we can define a quantity called the energy release rate or the crack driving force, though it is not a force, as minus del U del A, in which case this condition becomes G greater than Gc. So this condition will become, with this definition, G greater than Gc. This is absolutely similar to K greater than Kc, K1 greater than K1c for mode 1 crack propagation. So when the stress intensity factor is greater than a critical stress intensity factor, the crack grows. Here we say when the energy release rate is greater than a critical energy release rate, the crack grows. However, the units of K are different, the units of G are different. Units of K are, for example, MPa root meter. This is the unit of K. And the unit of G is Newton meter per meter square, energy per unit area, which is Newton per meter. Okay, so these have different units, these have different dimensions. Not only that, K is a measure that we have found from looking at the local stress state at the tip of an isolated crack. So K is the intensity of the stresses at the tip of a sharp crack. So it's a local measure of the severity of the crack, whereas G is obtained by integrating over the whole body. So it's a global measure. But then for linear elasticity, we will show that G and K are related concepts. We will show towards the end of this lecture, this week's lecture, that G and K are related concepts for linear elasticity, though one is a global measure and one is a local measure. So we have learnt about this criteria for crack propagation. Now we have this criteria for crack propagation, which says that the energy release rate has to exceed a critical energy release rate called Gc in order for the crack to grow catastrophically. One thing that has to be noted is that G has to be greater than only Gc, which is the energy required to form two new surfaces in Griffith's theory. No other energy cost is involved. When you do this bookkeeping here, you assume that in order to cause these crack extensions, all that you needed to supply was the surface energy required to form these new surfaces. So that is the only contribution this is this is an assumption inherent in the theory. The second point to note here is that the mode of the crack has not come into the picture yet. The crack can form anywhere. This additional crack may not form here, it may form somewhere else. It may form, the crack areas may form in some other places. So, this is just the bookkeeping of the total energy that is spent in forming the crack, nothing else. Where the crack forms, how the crack forms, in which mode it forms, is not there in the story at all. So I will stop here for this lecture, and then we will do a problem which will probably make it clearer for you what this concept is all about.